How many numbers does it take to specify a rotation in space? Think about it for 3 dimensions. You need 3, right? You can think about it in terms of axes, right? Any rotation, any general rotation can be broken down into one about the x-axis, plus one about the y-axis, plus one about the z-axis, right? This is pretty intuitive. Now, what about in 4 dimensions? How many numbers does it take to specify a rotation in 4 dimensions? It's got to be 4, right? Wrong. It takes 6 numbers to specify a general rotation in 4 dimensions. Why could this possibly be? So to talk about this, we have to talk about something called the special orthogonal group in n dimensions. So the way you can think about this is the set of all rotations in n-dimensional space, or Rn, where R2 is just the plane, right? You have 2 axes. R3 is 3-dimensional space as we normally know it, and so on. Rn has n perpendicular axes, and what we're wondering is, what is the dimension of this? That is to say, how many numbers does it take to specify a rotation, which I'm saying this group represents, in n-dimensional space? So the special orthogonal group, first and foremost, is a group. What does that mean? That basically means that for every element in this set, you have 3 essential properties. You have a way to multiply things, which you can think of as back-to-back rotations, and it has the associative property. So if you take one rotation and then the product of 2 other rotations, it's the same as first doing the product of these 2 rotations and then doing the last rotation. This is not true of all things, but it is true of rotations. Okay, so that's one property. A second property is that there is an identity, which is to say that you can do nothing. You cannot rotate it, and that action of doing nothing is part of this group. So we would write there exists, we'll just say E in SO of n, such that A times E equals E times A equals A for all A in SO of n. This is just a fancy way of saying doing nothing is part of the group. Okay, and then the third major property is that you have inverses. So an inverse times, or an element rather, times its inverse is equal to this nothing action. All this means is that if you do a rotation, you can do the complete opposite rotation and you'll end up exactly where you started. You think this is intuitive, but it's not true of all things. But these 3 properties, and I guess you could say the additional property that whenever you take 2 rotations, the end result is equivalent to another rotation. When you take all these properties together, you get what's known as a group. And we're not gonna appeal to the group nature too much, but you should know that. So the special orthogonal group is a special type of group. It's a group which is also a manifold, which makes it a Lie group. All that you need to know for the moment is that Lie groups are really special in that the vast majority of them have matrix representations. Let's do an example here. So SO of 2, this is the easiest one to understand, can be written as a matrix in this form, where it's parameterized by the number, if you will, theta. Pick any real number theta and plug it in to this matrix. What you get is a matrix which is an element of SO of 2. So we can represent these rotations as matrices. What does this mean geometrically? This means if you had your x-axis and your y-axis, and you want to rotate these 2 axes by an angle theta, let's call this x prime and y prime, then what you would do is you would take this matrix and you'd multiply it by the vector xy using matrix multiplication, if you know how to do that, and that will give you your new positions in your new coordinate system. So you can think of this matrix as a rotation. And in general, SO of n in n dimensions always has matrix elements. You can think of it as a matrix group, although it's not quite as simple as being parameterized in the way that this one is. Because the special orthogonal group has a matrix representation, we can, in essence, define it via its matrix representation. So its matrices are defined by two properties. Number one, that if you take a matrix that is in this group and you multiply it by its transpose, this is equal to the identity matrix, which is just the matrix which looks like a bunch of ones and then a bunch of zeros that are not on the main diagonal, which is right there. All right, so that is property number one, and this is the orthogonal bit. I won't get into that too much. The other bit is that the determinant of this matrix, if you know what that means, is exactly equal to 1. This separates it from just the orthogonal group, which can have matrices with determinant -1 as well. And so it's two path-connected parts. But SO of n is just the half of, if you will, which has determinant 1. All right, what's great about this group being a manifold is that we can find its dimension. And the easiest way for us to do that is going to be to find its tangent space. So let me just do that. All right, let P of t in SO of n be a smooth path in SO of n that goes through the identity matrix. For some t value, we'll just say t equals 0, this path goes through the identity, and it is differentiable so that P prime of 0 is going to be the tangent matrix, if you will, at the identity. Since P of t is in SO of n, we have that P of t times P of t transpose has to be equal to 1, just like all the other members of the special orthogonal group. Now we can do something fancy and take the derivative with respect to t of this equation. What are we going to get? We're going to get dp dt times P transpose plus P times dP transpose dt is going to be equal to the 0 matrix. Now, since it is always true that dP dt transpose is equal to dP transpose dt, rather, we can actually substitute this for this, and then if we plug in 0 for t, this means that P prime of 0 times P of 0 transpose. We also have that that P transpose of 0 is equal to P of 0 transpose, right? Those can be done in either order. Plus P of 0 times P prime of 0 transpose is equal to 0. But I told you that P of 0 is equal to the identity, because this path is passing through the identity matrix at time 0. So this is just the identity, this is just the identity, and what we're going to get is that P prime of 0 plus P prime of 0 transpose has to be equal to the 0 matrix. This is a very special property that only a few matrices in the scheme of things satisfy, called the anti-symmetric or skew-symmetric matrices. All right, that was step 1. We found out that tangent vectors to the special orthogonal group at the identity had to be skew-symmetric matrices. So there's one other fact. We have to use the other defining trait of the special orthogonal group, which is that the determinant is 1. We are going to take advantage of a very fancy map, which is the map from the tangent space to the manifold, and which you're already familiar with. It is none other than the exponential function. That's a discussion for another time, but basically we have this wonderful fact, which is that the determinant of e to the x for some matrix x is equal to e to the power of the trace of x, where the trace is the sum of the diagonal elements of the matrix. Because the exponential map goes from the tangent space to the manifold, or to the special orthogonal group in this case, we have that m is going to be equal to some e to the x for an x. Okay, so the determinant of that has to be equal to 1, which means that for x in the tangent space, e to the trace x has to be equal to 1, but this is only true if it's e to the 0 equals 1, right? So trace of x for x in the tangent space has to be equal to 0. So now we found our second defining fact of tangent vectors to the special orthogonal group, which is that they must have trace equal to 0. Now we're ready to describe the tangent space. All right, so I wrote our two defining factors of tangent vectors to the special orthogonal group right over here. And now we're going to look at examples of these for different dimensions. So let's set n equal to 2 first. So if n equals 2, this is going to be all the matrices of the form zeros on the diagonal, and x1 we'll just say here, and then negative x1 here. So it has to be anti-symmetric, right? So that if you take the transpose, which is where you flip everything, then you'll get negative x1. Well, you'll get the negative 1 up here and the positive 1 down here. And so element by element, you'll get 0, 0, 0, 0, 0, which is what we want. So for n equals 3, again, it's going to be zeros all through the diagonal. And then we have x1, and this determines the entry over here. We have an x2, which determines the flip entry there. And then x3. And these are all the negatives of those three. So now we see that this is equal to, you could write it as x1 times 0, 1, negative 1, and then zeros everywhere else, plus x2 times 0, 0, 0, 0, 0, 1, negative 1, 0, 0, plus x3, 0, 0, 0, 0, 0, 1, negative 1, 0. So this is to say that these three vectors, or matrices if you like, span the space, which means that it is isomorphic to R3. So it is a three-dimensional space. The tangent space is here. And what you need to know is that the tangent space always has the same dimension as whatever it's tangent to. So that means that SO of 3 has dimension 3, which is exactly what we expect, that rotations in 3 dimensions have 3 components. Now, how do we show that that's not true in higher dimensions? Well, we have to look at more of the general case here. All right, let's look at one more. So in the n equals 4 case, we'll do x1, x2, x3, x4, x5, x6, and then these are all the negatives flipped of those. I'm not going to write all of them down. But you notice that we have 6 entries which are independent variables. They can move however we want and they will satisfy these two properties. So that the tangent space to SO of 4 is 6-dimensional, and hence the rotation group in 4 dimensions is 6-dimensional. All right, so what's the general case? Well, notice what's happening here, that whatever is above the main diagonal, so this triangle of entries, those are all independent variables, whereas everything below the main diagonal has to be the reflected version of that. So what we do, what we're interested in then, is just counting how many entries there are going to be in a triangle of a given size. So for n in general, this is going to be the nth triangular number. So that is to say it's going to be 1 plus 2 plus 3 plus 4 plus all the way up to like k. And this sequence goes 1, 3, 6, 10, 15, 21, etc. Right? These are the triangular numbers. So that we find that the dimension of the tangent space, and hence the dimension of the special orthogonal group in dimension n, or not dimension n, sorry, well, in spatial dimension n, is going to be n times n minus 1 over 2. So what this is to say is, that using the tangent space to the special orthogonal group, we've determined that its dimension is n times n minus 1 over 2, or the number of coordinates, I guess you need, or numbers you need to specify a general rotation in n-dimensional space is n times n minus 1 over 2. A very unexpected result, but very cool.